Hello everyone. This week we're going to consider basic principles underlying design of neural networks. We're going to start with linear layers and consider some tips and tricks that allow improving their performance. So let's start with basic introduction into the design of neural networks and underlying learning principles. As you remember, in the previous lectures, we covered so-called linear models and how those models can be applied to the solution of more sophisticated cases when you don't have obvious linear boundary. For example, like on this picture, you see that blue points are sitting in the circle, and you cannot draw a single straight line that would separate orange from blue here. But if you add more features, like quadratic features in this example, you would map your dataset into the space that would allow drawing such a boundary. And basic intuition behind neural networks, if we add more sophisticated architectures, like layers connected to layers connected to layers, can we hope that some meaningful features will emerge during such concatenation and big number of parameters? So here is the very schematic representation. On the left we have raw features, and we feed into some model that designs better features, learns some meaningful representation, and then we send those good features into linear model, and it works as we discussed previously, giving predictions for another, for our case. And would it be cool if we could train those models, linear model and model for feature engineering, simultaneously? Because we can use the same idea of gradient descent if all those models are differentiable with respect to the error of a loss function on the given dataset. So what would it be if we use another linear model to design good features? Like on this picture, we have a dimension d prime here that maps the input features into some space d prime that in turn produces some prediction that we expect. So in that case, the prediction would be expressed in the form we have here, and if we substitute x wave with wx, then we end up with just another linear model, which doesn't make much difference with respect to a single linear model. So to make things a little more sophisticated, we can add a nonlinearity layer that would not allow to collapse two linear models together into a third linear model. So if we say that x wave is g, which is some nonlinear scalar function, applied element-wise to the wx, then it is no longer a simple linear regression. It is something else. So if we consider it with more details, we can say that we introduce those intermediate features of dimension d prime, and every element of this space is computed as a matrix of weights multiplied by input vector, and then we compute this nonlinear function on top of these elements, and we get vector of meaningful features that we can multiply with more weights, and we get the prediction. And we can simplify things a little bit by introducing a terminology when we have just weights matrix multiplied by input and call it a dense layer or linear layer. And we can call this element-wise multiplication of feature vector, element-wise computation of some nonlinear function as an activation layer or nonlinear layer. And usually those dense layers and nonlinear layer are combined together, because it doesn't make much sense to go with dense layers alone. And that's why those two are usually joined into a compound object that is called hidden layer. And this actually gives us some flexibility in the description of the higher complexity models. So we can decompose those into not individual neurons, weights, features, but into layers, which is a little bit more compact representation. Okay, so how do we train this complicated architecture? Actually, you remember what we did in the case of logistic regression or linear regression. In case of linear regression, we introduced a loss function that was representing the error that they get, and we wanted to make it as small as possible. In case of logistic regression, we introduced a maximum likelihood error, and we wanted to make it as higher as possible. But anyway, it is a kind of optimization problem that ties together weights that you want to find with data that you have and some meaningful representation of error estimation. Meaningful, at least in terms that you can judge how good your model is by looking at those numbers, and it is a differentiable thing. So in the simplest example, when you want to, for example, solve a regression problem, you can use a mean squared error loss function. And here you have representation of the same thing that we have written here. And we can compute the gradient with respect to all the weights that we introduced in this scheme. So if we say that loss function is a function that depends on the prediction f hat and ground truth labels, and f hat depends on those matrices W large and W low case, and you can compute the derivative of loss function with respect to those dense one layer weight, and to do so you have to use a chain rule. So if you want to compute derivative partial derivative of your function with respect to with respect to parameters of the function that your function depends on. It is a nested construct. You just do the following, like it is written here. Take a partial derivative of L by the nested function and multiply by nested function derivative by the weights you want to compute. And since you know that f is also a compound function, you have to repeat this procedure once again. So you add derivative of the dense 2 layer with respect to the activation argument, and then you add to or multiply it by derivative of the activation by the parameters of the dense one, and then you conclude with the final term, derivative of dense 1 by the weights of the dense 1. So the backpropagation algorithm is a propagation of the error from the final layers of your system to the beginning layer of your system, and this is why it is called backpropagation. And there are different algorithms that can do this in numerical way. Just we have to keep in mind that the operations that we performed here are inherently tensor based. So because they start with a scalar, and then you go into vector space, and you go into matrix space, and you go into tensor space. And well, basically because we operate with such a complicated weights in our function, but mathematically you do not notice such a complication. So let's have a quick look at different kinds of activation function that can be applied for those scenarios. So the simplest way is called a rectifier linear unit. So it equals to 0 if argument is below 0, and equals to the argument otherwise. Other example is exponential linear unit that is defined by this formula. Or it could be a soft plus that is defined by this formula, or it could be a sigmoid that we already know is used in logistic regression example, or it could be a hyperbolic tangent that is very similar to sigmoid, but it spans from -1 to 1, unlike sigmoid function that goes from 0. Notable difference here that some of those are restricted on the range like 0, 1 or -1, 1. And it means if the argument of this function is far away from 0, your gradient becomes negligible. So because it is essentially flat in this region. So if it's higher than 10, then you get 0 gradient effectively. And some functions like rectifier linear unit or exponential linear unit or soft plus, those are not restricted, and it means that they are okay to pass the gradient for numbers, values as high as you want. Although you also may notice that some of those functions are restricted by 0, and for example, for negative values, none of those is able to produce a meaningful gradient. So it means that it works nicely if your values are positively defined. So combination of linear layers and nonlinear functions allows us to build a much more powerful set of approximator. So there is a mathematical notion of so-called universal approximator that essentially is a combination of those two layers. And a dense layer connected with activation layer that we annotated as a hidden layer before. Or given the possibility that we can put as many dimensions into this hidden layer, we can build a function that would be arbitrarily close to any other given function. And however, in practice, finding such approximator is not always a feasible thing because of the different details like heavily non-convex loss functions or requirement to build a very high-dimensional intermediate representation and sometimes overfitting of such a function. So in practice, it is more meaningful instead of growing large number of neurons inside those hidden layers, we can attach one layer to another, thus building so-called stacked architecture, similar to one we considered during the decision trees lecture. And there are many ways how you can attach those layers one to another. There are different ways how you can play with dimensions of those layers, and etc. etc. So in the next lecture, we consider how those layers can be organized to address working with images, problems of shift and variance of images. So by stacking more layers together, we effectively reduce number of neurons that is required to train such a function, thus reducing possibility of overfitting. So, what kind of optimization techniques can be used to find an optimum of the loss function? So, you remember the approach that we considered that is called gradient descent, and the variation of this approach that is called stochastic gradient descent. And imagine a function space that it has to space that produced by a loss function given weights that we want to navigate using those algorithms. It might be a quite complicated undertaking. Thus, many different modifications exist to help to improve the accuracy of such training. So first, I would mention SGD, stochastic gradient descent, on mini batches. Remember, stochastic gradient descent at every step k picks a single element at random and then computes the loss function. For this particular element, computes the gradient and updates the weights of the predictor in the direction opposite to this gradient. So which makes this method quite noisy. To make it more stable, we can shuffle the training set and then iterate through it not by element, but in chunks or batches of fixed size. And at each iteration, we evaluate the loss of this gradient given the chunks. So we computed for the vector of the elements of the chunk. and update the gradient accordingly. Update the weights according to this gradient. And another idea is we can introduce like artificial inertia in this space of the movements of this gradient. So you see, in case you start from here and you fall down the valley, you start to oscillate according to this axis, because you have some kind of tangential component of the movement. And if you imply the intuition of a ball rolling down the hill, you may add one more parameter to this trajectory that would correspond to the speed of the ball, that is not defined only by the inclination, but also defined by its previous speed of the previous time step. Right? And if the ball falls down like this, it would produce much smoother trajectories. Also, it will not stuck into some unneeded, unphysical local minima. Another extension of the gradient descent method is RMS prop. So idea is adjusting learning rate separately for different components of the parameter vector. So if gradients are getting smaller, we can increase the learning rate. That means that we can make a more meaningful steps and go through the flat regions of our loss function valleys. And so here is a little bit of math, how those gradients are estimated. And another optimizer, it is called ADAM, or adaptive momentum, that combines both ideas of momentum and RMS prop, and usually it serves a pretty good choice of an optimizing algorithm. So in this picture you see how different algorithms converge to a certain minima, and you see that ADAM and RMS prop are like leaders in this case. So it brings us to a conclusion. We have covered neural network basic principles that are built on top of individual building blocks that are called layers, representing linear models and some nonlinear function. And this architecture intuitively allows us to extract a meaningful feature representation from our data. And thanks to such compound architecture, neural networks can approximate any function arbitrarily well, given they are deep, wide enough, and we have enough of data. And loss function in that case typically become highly non-convex, and it makes optimization procedure a bit harder than optimization of a simple logistic regression or linear models. And to deal with this problem, a variety of gradient descent modifications are available. So one thing that you can think about meanwhile is, can neural nets really solve every possible supervised learning problem? And another thing to assess yourself, you can answer the question about weights initialization before training. And in the next episode, we're going to cover this topic in much greater details.